Hello everyone, and welcome back to Chem Story. Today we're diving into formal charge and why it really matters when you're working with Lewis structures. If you've ever asked yourself, how do I know which arrangement of atoms is best in a molecule? Well, formal charge is one of the first things you need to look at. It helps us figure out which structure is the most stable, and that's super important when we're trying to predict how a molecule is going to behave. So, what exactly is formal charge? It's kind of like a bookkeeping tool, a way to assign a hypothetical charge to each atom based on how the electrons are shared. Now, it's not the real physical charge on the atom, but it helps us analyze how electrons are spread out in a molecule. And more importantly, it helps us figure out which Lewis structure makes the most sense. You can think of it this way. Formal charge tells us how much charge an atom seems to carry, depending on how the electrons are divided up. It gives us insight into the electron distribution, and that's what helps us choose the most stable structure. And here's the key part. When you add up the formal charges of all the atoms in a molecule, that total has to match the actual charge of the whole molecule. So for a neutral molecule, the sum should be 0. And if you're dealing with a polyatomic ion, the total should equal the ion's overall charge. That's something you always want to keep in mind when you're drawing Lewis structures. So why do we care about formal charge? Because it helps us figure out which Lewis structure is the most stable, especially when there's more than one possibility. When a molecule has multiple valid Lewis structures, the one with the smallest formal charges, meaning the charges are closest to 0, is usually the best. If there are formal charges, we want to keep them as low as possible. And here's another key point. Negative charges should go on the more electronegative atoms, like oxygen or fluorine. Positive charges, on the other hand, should be placed on atoms that are less electronegative, like carbon. When a Lewis structure follows these guidelines, it's much easier to tell that it's the most reasonable and most stable version of the molecule. To calculate formal charge, there's a simple formula you can use. Start with the number of valence electrons the atom has when it's neutral. Then subtract the number of non-bonding electrons, the ones it keeps to itself. After that, subtract half of the bonding electrons it shares with other atoms. And that's it. The result is the formal charge. Straightforward, right? Another way to think about formal charge is by comparing what an atom normally has to what it actually owns in a given structure. Every atom has a certain number of valence electrons when it's neutral. That's our starting point. Now, in a Lewis structure, the atom owns all of its non-bonding electrons because those aren't shared with anyone else. And for the bonding electrons, since those are shared, each atom gets credit for half. So formal charge is just the difference between what the atom normally has and what it ends up owning in the structure. It's a helpful way to check whether the electrons are distributed in a way that makes sense, based on what we expect for each atom. When you're doing the calculation, you can just look at the periodic table to find how many valence electrons each atom has. It's a quick and easy way to get that starting number you need for formal charge. Now let's put all of that into practice with an example. The nitrate ion, NO3-. In this structure, nitrogen is in the center, bonded to 3 oxygen atoms. One of the oxygens is double bonded to nitrogen, and the other 2 are single bonded with extra lone pairs. Nitrogen normally has 5 valence electrons. But in this Lewis structure, it doesn't have any lone pairs, and it's involved in 4 bonds, which means it's sharing a total of 8 bonding electrons. Since it only gets credit for half of those, nitrogen effectively owns 4 electrons. So if we plug those numbers into the formal charge formula, 5 minus 4, we get a formal charge of +1. Each of the 2 single-bonded oxygens normally has 6 valence electrons. But in this structure, they each have 6 non-bonding electrons, plus 1 more from the single bond, since they get half of the 2 shared electrons. That adds up to 7 electrons they own, so when we do the math, 6 minus 7, we get a formal charge of -1 for each of those oxygens. The double-bonded oxygen also starts with 6 valence electrons. In this case, it has 4 non-bonding electrons. That's 2 lone pairs, and it's involved in a double bond, which means it shares 4 bonding electrons. Since it owns all 4 of its non-bonding electrons, plus half of the 4 shared ones, that's 2 more, it effectively owns 6 electrons. So 6 minus 6 gives us a formal charge of 0. When we add up all the formal charges, we get +1, -1, -1, and 0, which gives us a total of -1. And that matches the actual charge of the nitrate ion. So this confirms that the structure is correct. Remember, the best Lewis structure is the one with the lowest formal charges overall. And if there are any formal charges, the negative ones should go on the more electronegative atoms, like oxygen, while the positive ones should be on atoms that are less electronegative, like nitrogen. Once you get the hang of this, picking out the most reasonable structure becomes way easier. So to wrap it up, formal charge is a super useful tool when you're trying to figure out the most stable Lewis structure. It gives you a clearer picture of how electrons are distributed and helps you compare different possibilities. The main thing is to keep formal charges as small as possible and make sure they line up with what we expect based on electronegativity. And the more you practice, the more natural this process will feel. Try it out with some other molecules and see how well you can predict their structures. Great job today. Keep practicing, and I'll see you in the next lesson.